Hi everyone, Heapified here. In this video series, I want to start talking about some operating system concepts that often come up in real-life practice. In this first video of the series, I'm going to be talking about system calls and file I/O. One really good way to see how your operating system works is to try programming in C and see how your compiled code gets converted into an executable that your computer can actually run. In this first video of the series, we'll take baby steps and learn about system calls and file I/O. Although we'll be using C in this video, much of the same concepts apply to other programs, just that other languages often try to hide the raw interface with the operating system from you, and we'll talk about how that interface looks. Most of what I say here applies to Linux and Mac or any UNIX variant, and may be hard to generalize if you're on Windows, but most of the principles are the same. All of your computers have an operating system that provides a set of core functionalities, like providing file I/O, access to the internet, providing scheduling for processes and threads, and so many more features. The programs that software developers write run on top of the operating system and make use of the operating system functionalities to perform their application level goal. Now, very often, an application will want to perform an action that only the operating system has the authority to perform. For example, if you want to read a file on disk, your application can't just directly access the file. Instead, your application has to talk to the operating system, which will perform a series of checks. For example, it makes sure that you're allowed to read the file or to write the file. And then, if you're allowed to access the file, the operating system will perform the action you requested. For example, when you want to read a file, you perform something called a syscall. That is, you instruct the operating system that you want it to read a file for you, and you tell the operating system which file you want to read and where to put the results of the read operation. Then the operating system will check that your application has the right privileges to read the file, and if so, it'll read the file on your behalf. In most computers, your processor has a user mode and a kernel mode. The user mode is the mode in which most of your applications run. This is the default unprivileged level. On the other hand, the kernel mode is a special privileged level that allows certain functionalities to be unlocked, such as directly accessing the file system. The operating system kernel is the part of the operating system that runs at this privileged level and performs actions requested by user programs or even sometimes other parts of the operating system. For a user program to tell the kernel what to do, the user program has to execute something called a syscall. A syscall, short for system call, is just an action that requires special privileges to complete, and these privileges are usually only given to the operating system kernel. Therefore, your application tells the operating system what operation it wants it to perform, and the operating system will go and do that for you. We'll take a look at some syscalls using the example of file I/O. In this case, I want to build a very simple clone of the cat and cp commands. Cat just reads a file and prints the output to the console, and cp copies one file from a source to a destination file. Okay, I'm here in a new directory that contains just one simple file called readme.txt, and if I run cat on readme.txt, it'll just print out the contents of readme and print it to the console. Now, in this tutorial, I want to write my own cat from scratch, and it'll do very basic functionalities. It won't have any special options. It'll just read the file and dump it to standard output. To get started, let's create a file called cat.c. To actually execute syscalls, I need to include a few things. So I'm just going to include a few files. Okay, these files provide certain constants and function stubs that we'll use later. Alright, now let's create a main method. So int main int argc *** argv. This is the standard function signature for a program in C. Argc is just the number of arguments supplied on the command line, and argv is the actual arguments to the program. Now, it's convention that the first argument to a program is always the name of the program itself. This might sound kind of funny, but it occasionally comes in handy. So in our case, we want our cat program to take in one argument on the command line, which is the name of the file we want to print. So this means that I actually want to check if argc is less than 2, because remember, the first argument is the name of the program itself, and the second argument will be the file that we want to read. So if argc is less than 2, then let's just print out an error saying not enough arguments, and let's return -1. See how main returns an integer? The integer that main returns will be the program's exit code. All programs have an exit code. Normally, returning a 0 exit code means that everything happened normally, and you can use the exit code itself to encode what error happened in the program. But in this case, we'll just return -1. Now in Unix operating systems, all file I/O happens through a very controlled interface. Before you can do anything to a file, you have to call open. The open syscall is the one that usually checks permissions and makes sure you're allowed to access the file. Then there are two syscalls, read and write, that allow you to read or write the file respectively. Finally, once you're done with the file, you need to call close. The close syscall basically just frees up any memory that your operating system allocated to open the file. So let's see how the open syscall works. To call open, I can simply type open, and the first argument is the name of the file. So in this case, we want to just open up the first argument. And then open takes a set of flags indicating what you want to do with the file. In this case, I want to be able to read from the file and print it to the standard output. So I'm going to tell C that I want to open this file in read-only mode, like so. The read-only constant tells your operating system that you only want to open the file and read from it. You won't be able to write from the file if you open it in read-only mode. Open returns something called a file descriptor. A file descriptor is just a non-negative integer that your operating system uses to keep track of which files your program has opened. So let's create a variable to store our file descriptor. So let's say int fd for file descriptor, and then let's say fd equals open, like so. Now the way the operating system tells us if there was an error opening the file, for example if the file does not exist or if you don't have the right permissions, is by returning a negative file descriptor. So the way we can handle that case is by saying if fd equals open less than 0, and C, an assignment statement like fd equals open with the arguments returns the value that was assigned. So in this case, if fd is assigned a negative value, then this if statement will be true because, for example, -1 will be less than 0, and then we'll know that there was an error and we have to handle it appropriately. So in this case, let's just use the function called perror and say fail to open file. Perror will print out a string, in this case fail to open file, along with the description of the error that occurred. And if there was an error, let's just return -1. Okay, cool, we have an open file. Now let's actually read the file. In order to read the file, we need to tell C where we're going to store the bytes that are read from the file. So let me create a buffer, char buff, and let's give it a size of buff size. At the top of the file, let's add a define buff size to be, let's say, 128 bytes. This is kind of small, but it's fine for now. So this just says create a character array of size 128 bytes, since each character is 1 byte. Okay, now let's call the read syscall. So read takes in the file descriptor, so this tells your operating system which file you want to read from. Then it takes in the location where you want the results to be stored. In this case, we want to store the results in buff, so let's pass in buff. The last argument is how many bytes you want to be able to read. In this case, I want to read up to buff size -1 bytes. The reason I'm putting a -1 here is because later I'll want to append a 0 to the end of the buffer to mark it as null terminated. The null terminator is just a 0 byte at the end of a string that tells C, hey, this string ends here. If we try to print out a string that was not null terminated, we might read beyond the bounds of the string array, and this could cause the program to crash. The read syscall will return how many bytes were read from the file. So let's create a variable to store that, int bytes read, and let's set bytes read equal to read. And now read will always continue to return a positive number until we reach the end of the file or an error occurs, in which case 0 or a negative number will be returned. So we can check for that in a loop. So let's put this in a while loop. So while bytes read equals read greater than 0, and then let's print, and inside the body of the loop, let's print out what the contents of the buffer are, like so. What this basically says is, while the number of bytes read is positive, keep reading the file and printing it out. The only reason the bytes read would be 0 or a negative number is if we reach the end of the file or an error occurred. So this is fine. And then I need to do one more thing, which is I need to mark the end of the buffer with a 0 byte. So we'll say buff bytes read equals 0. This just says if we read 10 bytes, mark the 11th byte as 0. Remember that arrays are 0 indexed. So if we read 10 bytes, then buff10 will be the 11th byte, and so we should mark that as the null terminator. This way we don't print out more than we actually read from the file, and in particular we don't try to print out a non-null terminated string. Okay, this should be it. It's generally good practice to close files once you're done with them, even though technically once your program exits, the operating system should clean up any files you left open. So we can do that by typing close fd. So we close the file that we had open, and then let's return 0 because if we reach the end of the program, then things probably went normally. So let's do that, and then let's close main and save and quit. I'm going to make a make file to make it easier to compile these programs. If you haven't watched my previous video on make, you can do that to see how it works, but it doesn't matter too much. This will just compile the program using GCC, and then we'll be able to run it. So let me just write out a quick make file. Okay, so this is how my finished make file looks. I have two main targets here. There's cat, which we just wrote, and there's cp, which we'll write next. So let's save this and quit, and let's type make. Alright, and you can see that we have an executable, so let's try this. So I'm going to do /cat, and then readme.txt. And you can see it prints out the readme, just like the normal cat command. Let's see what happens if I try to run the program on a non-existent file, this /cat a. And you can see it prints out our error message, failed to open file, followed by a description of what error happened. In this case, no such file or directory. So that's great, that's exactly what we want. So we've now seen how to read files. Let's look at how to write or create files next. Okay, let's write our next program, cp. To start, I'll just copy my cat.c program into a new file called cp.c, and then let's edit cp.c. Okay, so in this case, I want my program to take in 3 arguments. So let's change that to 3. The first argument, as usual, is the name of the program. The second argument will be the name of the source file, and the last argument will be the name of the destination file. And then our program will just copy the source file into the destination file. So now let's change fd to, we're going to have 2 file descriptors. Let's call them source fd and destination fd, like so. And then let's change this to source fd. Okay, now we need to also open up another file that will be our destination. In this case, we can do the same thing basically. Dest.fd equals open. This time we'll pass it argv2, the third argument. Okay, now we need to tell our operating system that we want to be able to write to the file. We can do that by saying o write only, like so. Now there are a few other things we want to happen. If the file doesn't exist, we want the operating system to create the file. We can do that by passing in the o create flag. The OR symbol just means we're going to do a bitwise OR. These are like 2 integers, and doing the bitwise OR basically means to combine both the flags. So in this case, we're going to mark the file as write only, and we're going to create the file if it doesn't exist. The last thing we want to do is, if there's already some stuff in the file, we want to overwrite all of that. So we'll pass in the o truncate option. And the truncate option basically says, if there's anything in the file already, delete it once I open the file. Okay, the next thing we need to do is, if you open a file with the o create flag, the operating system needs to know what permissions the file should have. I'll make a separate video about UNIX file permissions, but in this case, I'm just going to say the file is readable and writable, like this. So the SIR user says writable by the user, and the SIW user says writable by the user. All right. Again, we should check if this is a negative number. If so, then an error happened. And then let's, if this error happens, we'll close up the source file descriptor that we opened before. Let's print out the error again, failed to open file. And let's return a negative exit code. Okay. Just like the read syscall returns the number of bytes that were read, the write syscall returns the number of bytes that were written. So let's create another variable for that, int bytes written. In this case, I'm not going to be printing out the string to standard output, so I can just read in the full bus size. We're not going to be printing out a string, so we don't need it to be null terminated. All right, let's also delete this line since we're not null terminating the string, and let's delete the printf. Okay, now I want to actually write to the file. So the way I can do that is by calling the write syscall. Let's call write, and we want to write to the destination file descriptor, so dest.fd, and then write takes in the location of the memory that you want to write. In this case, we read data from a file into buff, and we want to write buff into the destination file. So let's put buff here. Okay, the last argument is the number of bytes that we should write to the file. You might think that we want to write buff size bytes to the file, but that's not correct, because what if we read less than bus size bytes? So actually the number of bytes I want to write to the file is the same as the number of bytes I want to read to the file. So I'll pass in bytes read. The write syscall returns the number of bytes that were written to the file. So if I end up getting a result that's different from bytes read, I know there was a problem. Maybe the operating system doesn't have enough space to write more to the file, or some other error occurred. So let's check that in an if statement. So let's write if bytes written equals write, and let's check if this is less than bytes read. If this happens, let's printf failed to write. Let's close both file descriptors, source ft and destination ft, and let's return a negative exit code like this. Once I'm done with both files, I should also close them up like this, and let's also close the destination file descriptor like this, and let's save and quit and try that out. So I'll run make. Okay, it says I have an undeclared identifier ocreate. That's because it's not actually ocreate, it is ocreate minus the e. So let me change that. Okay, let's save and quit. Okay, I also forgot to change ft to source ft. Let's do that real quick. So we're reading from the source file. Save that and quit and try again. Okay, there we go. By ls you can see I have a cp executable here. And now let's try executing that. So /cp. The source file we'll read from is readme.txt. And let's put that in a new file called newfile.txt. Like this. Alright. And now I can run my own cat program on new file. And you can see that the readme was copied into the new file. Okay, so hopefully this makes sense. You've seen how to do read and write syscalls along with open and close. And you've seen how C uses these syscalls to manage file interfaces. Even though this tutorial was in C, all languages use read and write syscalls when they perform file I/O, even if they don't necessarily call the application level functions read or write. In later videos, we'll talk about other operating system concepts such as processes and threads and networking. Alright, that's it for this video. I'll see you in the next one.